Hi, in this video I'm going to explain how a resting potential is established across the axon of a motor neuron. So first, nerve impulses, which is a term we use to describe the action potential and then the transmission of that action potential. They're caused by the movement of sodium ions and potassium ions across the axon membrane. So there's a couple of little things to note here. You must refer to them as ions. This isn't the movement of sodium or potassium, but sodium ions or potassium ions. Now you can shorthand that to Na plus and K plus. That's absolutely fine. The nerve impulse itself can be summarised in 4 parts. First, a resting potential must be produced across the membrane of the axon in preparation for what comes next, which are depolarization, repolarization, and hyperpolarization. Now parts 2, 3, and 4 there, depolarization, repolarization, and hyperpolarization is what is referred to as the action potential. And I'll follow this video with another one about the action potential after. Okay, so before an action potential can be produced, a neuron must be prepared. We say it's in the resting potential is established. Now this is a potential difference, so the difference in charge either side of the axon, of minus 70 millivolts. So the inside of the axon is negative compared to the outside. It has this minus 70 millivolt potential difference. And we can say when the neuron is at resting that it is polarized. For a nerve impulse or an action potential to be transmitted, the potential difference is temporarily reversed. And that's a word to look out for in the exam questions. They often talk about the reversal of the polarity or reversal of the charge. And that is achieved when sodium and potassium ions are exchanged across the membrane. The potential difference becomes less negative and then becomes positive up to a value of plus 40 millivolts. And when it reaches that state, we say that the membrane is polarized. So you will read, depending where you read that these values differ slightly. But for AQA, just assume that the resting potential is minus 70 and the potential difference at the highest sort of amplitude of the action potential is plus 40 millivolts. Okay, so this is my membrane. The membrane contains a number of different proteins. The first 3 proteins that we're going to look at, this one, and this one, are important in establishing the resting potential. So this protein here is known as the sodium-potassium pump, and its role is to actively transport sodium ions out of the axon and potassium ions in. So let's just add a few labels here. This is the outside of the axon, so it's surrounded by tissue fluid. And this is the inside of the axon, sometimes referred to as the axoplasm. Okay, the axoplasm, just another term used to describe the cytoplasm, but specifically inside a neuron. The sodium-potassium pump, as it suggests, is involved in active transport. So it uses ATP and the hydrolysis of ATP to provide energy for the active transport of these sodium and potassium ions. It does it in a very specific way. So it actively transports 3 sodium ions out for every, that pen's not very good, every 2 potassium ions in. Pen's a bit squeaky, and it's not very clear. Let's see if this one's any better. A little. Okay, so that's 3 sodium ions actively transported out, 2 potassium ions actively transported in. Sometimes it's referred to as an exchange pump. Okay? So move them by active transport to the outside and the inside. Now the effect of this active transport is continuing all the time, is that it creates a high concentration or a higher concentration of sodium ions on the outside of the cell than on the inside. So I'm going to use square brackets here to represent concentration. So we get a higher concentration of sodium ions on the outside. And I've used the little bit there to demonstrate that this is comparative. So this is a concentration gradient being established. Higher sodium ion concentration on the outside. On the inside, we end up with a higher, again, concentration of potassium ions. Okay, so far, active transport, 3 sodium ions out for every 2 potassium ions in. Higher concentration is created on the outside for sodium ions, higher concentration on the inside for potassium ions. Now next are these 2 proteins. Now these are referred to as leaky channel proteins, or leaky channels. So on the right here, this red one, this is a leaky sodium ion channel. On the right, we've got a leaky potassium ion channel. Okay, now you don't need to use this term leaky for AQA, but you will see it in certain textbooks and online and things, and it quite nicely demonstrates what's going to happen next. So these leaky channels, the reason they're called leaky is they're always open, and they allow the diffusion of some of these ions down their concentration gradient. Okay, so we've got a higher concentration of sodium on the outside. That allows some, and I emphasise some here, sodium ions to diffuse back down their concentration gradient. The potassium ion channels are much more common. They're much more frequent in the membrane. So if we can imagine for every 1 sodium ion channel, there are approximately 100 potassium ion channels. And that means the membrane is much more permeable to the diffusion of those potassium ions out. I'll use that rubbish pen again. Oh, that was even squeakier. I'm sorry. Okay, so this establishes a potential difference across the membrane. What we end up with is an accumulation of more positively charged ions on the outside than on the inside. Okay, because we've got a lot more potassium ions diffusing back out, and to begin with, the sodium potassium pump is exchange 3 of those positively charged sodium ions out for every 2 positively charged potassium ions in. So, the inside of the membrane becomes negative compared to the outside. And that's where we get that value of minus 70 millivolts. Okay, so we say that the potential difference across that membrane is minus 70 on the inside compared to the outside. Okay, so these 3 points can be summarised, and often the question will be describe how the resting potential can be established. So you just go through it step by step. Number 1, the sodium-potassium pump. Sodium-potassium pump. Now we need to refer always to the type of transport. So sodium-potassium pump actively transports 3 sodium ions, and I'm emphasising here that these are ions. Na plus would be fine, but I'm just sort of belt and bracing it here. 3 sodium ions out, and 2 potassium ions in. Okay, so we've got a few things in this sentence. We must refer to active transport. We must refer to ions, and obviously you need to get the direction of those ions the right way round. Sodium ions are moving outwards, potassium ions are moving back in. In the exam, you wouldn't actually have to include this 3 and 2. So if you're likely to confuse those, just leave it out. Okay, it's safer to forget the 3 and 2, just go with sodium ions being actively transported out, potassium ions actively transported in. Okay, so the second thing we can say, now this second part relates to the permeability of the membrane to sodium ions and potassium ions. Okay, so number 2 then. In fact, no, I'm going to go back a step. You could do it that way, or you could do it this way. Let's say that the second part is this establishment of these 2 concentration gradients. Okay, so number 2, we have a higher, and make it comparative, concentration. Please don't abbreviate concentration in the exam. You won't get away with it. Of sodium ions outside and a higher concentration of potassium ions inside. Okay? Now, coming back to these leaky channels, third part here. Because there are more potassium ion leaky channels than there are sodium ion channels, we can say that the membrane is more permeable to the diffusion. Okay, I'm stating the type of transport again, of potassium ions moving back out than sodium ions diffusing in. Okay, and that really explains how this resting potential is established. Okay, right, so here is a question. I'm going to have to wipe this off the board, aren't I? Here is a question. Describe how resting potential is maintained in a neuron. Okay, maybe pause the video now, go and have a cup of tea. Don't just do it straight off the bat. Come back and have a go at answering that question. I mean, I know I've given you the response, but now is your opportunity to practice and to get it right. Okay, so pause your video now, do what you need, and we'll come back in a second. Right then, we're back, if you went away at all. So, how is a resting potential maintained in a neuron? Sodium ions are actively transported out and the potassium ions transported in. Okay, so we're mentioning ions here. We have used sodium instead of Na+, but ions makes that fine. Given the correct direction, sodium ions out, potassium ions in, and we've referred to active transport. Now, here, this is that 3 sodium ions out for every 2 potassium ions in, but just be careful of this. This was on the AQA November 2021 paper. They rejected it if the numbers used were incorrect. And also, if you do this in your essay, and you get the numbers wrong, it would be counted as a fundamental error. That creates a higher concentration of potassium ions on the inside and a higher concentration of sodium ions on the outside. Again, we've got these comparative errors to show the concentration gradient. And then the membrane is more permeable to those potassium ions diffusing out and sodium ions diffusing in. Here are a few little points. This was on the mark scheme in the little comments. Must make a reference to the ions or give the charges on the symbols. If mentioned once, you can allow it for all of the points. I would do it every time if I were you. If the answer provides 2 or 3 of the mark points without any reference to the ions, you'd only get a maximum of 1 mark. Okay, we're not talking about the transfer of little lumps of metal. It is about the transfer of those ions. Okay, so that's the establishment of the resting potential. In your notes, page 15, you've got a similar diagram. There's just a few little bits on this diagram to highlight, really, to emphasise. So, starting over here, that the charge is more negative on the inside, more positive on the outside, so minus 70 millivolts. The inside has this high concentration of potassium ions, and if you've been following along, you'll know you can make that higher to make it a concentration gradient. Higher concentration of sodium ions on the outside. Now, here is that idea. More channel protein molecules for the potassium ions. Here's the idea that it is more permeable to potassium ions diffusing out. Okay. 3 sodium ions actively transported out for every 2 potassium ions actively transported in. Oh, yeah, and there we go. One last little note on this. Sometimes just describing the process isn't quite enough. You might need to apply your understanding. And one common way they'll do that is with a reference to a respiratory inhibitor, or cyanide, or something else. With a respiratory inhibitor, as in all questions, that's going to prevent respiration. Therefore, there will be less or no ATP, And in this instance, less or no ATP means that sodium-potassium pump is unable to do the first step. It's unable to move 3 sodium ions out and 2 potassium ions in. So there will be less, I've got it the other way around now, no or less active transport. In this case, if active transport is stopped completely because there is no ATP, eventually all of the ions will diffuse down their concentration gradients. So all of the sodium ions will diffuse in until they reach equilibrium. Potassium ions will diffuse out until they reach equilibrium. And the membrane potential then would equal 0 millivolts. The potential difference after the respiratory inhibitor has prevented respiration so that there's no ATP and no active transport, eventually the potential difference would reach 0 millivolts. Okay, right, that's everything I'm going to do on the resting potential now. I'll make another video afterwards for the action potential. Cheers.